right. Good morning, good afternoon, everyone. Thanks for joining today's call in partnership with Team D3 and Altair. Today we're going to talk more about the designing, simulation-driven design, smart design, and advanced manufacturing solutions, especially how to connect this design and the manufacturing sides together. My name is Jaideep Bangal. I'm a senior director at Altair, focusing on our simulation-driven design and manufacturing solutions. In different words, we call it as an Inspire platform. So let's get started. First thing first, why when we talk so many times about design, simulation, or manufacturing, right? There are many reasons, and there are many challenges that our companies, our engineers face today. Competition. Competition from your various countries, various regions, and maybe it's a startup coming up with a new idea. Complexity. Things are getting very complex. Maybe in a few years back it was simple. You create a car, we make standard parts. Now it's all about electronics. It's all about AI integrated within the car itself. So the things are becoming complex, and hence the more need of new technology. And of course, product time to the market is very crucial. It was always crucial, and it's more important now. I have a company, automotive company, who wants to squeeze their product development cycle for a particular developing an entire car from 3 years to 15 months, right? How to do that? Can we just employ, twice as many engineers and it will work? Maybe, but that's not cost-effective solution. So the next cost-effective solution is include the technology that's available for these engineers right now. Now, saying that, even the engineers face challenge. Maybe it's a design challenge, maybe it's a efficiency for the design. What happens is simulation. When to use the simulation tools? Should I use it early in the design phase? Should I use in the mid, or should I send it at the end of the design or product development cycle? Many engineering companies have done this are implementing simulation tools very late. The design engineers design the part, then send it over to the CA engineers, manufacturing engineers, to see if they can make it. They send the report back saying make those 5 changes. Is it efficient? That's not. And that's where, can I make these tools available for the design engineers, mechanical engineers, to be used very early in the design phase? That's becoming very important. Now think about this. This is a report from Wall Street Journal, WHJ. Chinese companies are 30 to 50% quicker, car companies, and they're becoming threat to a lot of automotive companies here in Americas or the Europe. I mean, they're doing the right things. But there are a lot of those companies are my customers, our customers. We are helping them to move faster. The way they are moving faster is implementing these design tools, AI tools, manufacturing solutions very early, to predict the failures and fix those failures during the design phase. Another example on the manufacturing side is this is a Shiva tool take from Asia. They were able to reduce or predict the failures, casting failures, manufacturing failures very early. Almost, they're saving 80% of their time, the product development cycle time and the manufacturing time right now. This is another example from the aerospace company who wanted to redesign their part, make it lightweight, use a different materials. They wanted to use different manufacturing process, but of course, because it has to go through FAA regulations, they cannot just change the manufacturing process or use totally different material. So what to do? So they implemented this topology optimization based on the loads, loading conditions, worst case scenarios, and then they 3D printed the sand mold for this part, which eventually they casted that part. So they're using base from both the worlds, from 3D printing or from optimization, come up with a lightweight design, but also use this traditional manufacturing process, which is proven and go through the regulations very quickly. So with that just one part, they were able to save 3 pounds, and that's about 60 plus 65% reduction in the mass savings. Now, another example, maybe it's the last example I want to show, but I'm going to tell you now, you can get the crisp of the story. Is it's also important to design the part for a manufacturing process. It's not just the finding the defects during the manufacturing, but can I predict those defects at the manufacturing level, and can I make design changes or maybe change process changes for to get the successful manufacturable part. This particular design, it was 8% mass reduction. But the question always get, all right, that looks good on the paper, PowerPoint presentation. So what, right? My applications, my designs are different. So what we can do is we start kind of dive deep into the how it works. You know, find the downstream problems very early. Maybe change with the one component. Maybe start change with one process element, and to see if that benefits your application. So what is design, or we call design for manufacturing, design to manufacturing? It's a solution. So if I'm an engineer, there are two ways engineers design part. Designing from scratch with a napkin sketch, where the forces are, loads are. This is my area where I want to design. The second way method is very common. It's carry over design. That design is there for a long time. I want to make design changes now. Maybe use different material, different manufacturing process. So I always start with the exist how this part behaves today, right? Going to run quick baseline simulation. From there, I will start with the largest possible design space, packaging space available for engineers. And then from the given loads, which can automatically be calculated or populated as a load cases from a kinematic motion simulation, which you see on the screen. So it's a simple motion simulation with the springs, hydraulics, and no, this is with the bracket for the Ducati Superbike. Now, those moments and forces are calculated on joints, pins, force locations, and are going to use those as my load cases. And the tool come up with the most optimal solution. This is where the material needs to be. Right? That's what the tool is telling me. But how am I going to manufacture this? Is it manufacturable? Maybe machining, maybe 3D printing. But even with 3D printing, it's not that easy to design that particular design what we see on the screen. At that point, we force the tool to come up with a design which is manufacturable. Maybe it's different manufacturing processes. Maybe it's injection molding, machining, the 5-axis mill, 3-axis mill. Maybe it's LED manufacturing. Maybe it's a casting, single draw, split draw. Maybe it's a stamped component. And depending on my manufacturing process I select, or multiple manufacturing processes I select, the tool will come up with the design which is for casting in this particular case. And before I go do anything to this part, I want to run quick manufacturing feasibility simulation. In this case, I want to run a quick casting simulation. I'm still an engineer, design engineer working on my laptop, but I want to find out if I cast this part, is it going to make it? Or am I going to get porosities, or I'm going to get failures? If I get the failures, I predict the failures from the simulation, I can go back, make quick design changes in the same exact process, and see if I can avoid those defects. Or I can make start process changes as a part of my casting process. So there are different ways to use this and predict those failures. But finally, once my design is kind of locked in, I want to quickly check validation performance. How I'll put the new design into the same exact baseline I started with, and I want to see if this design satisfy my criteria, and finally send it to the manufacturing. So that is kind of in a life cycle of a part, or a product, right? In theory, it's great. It goes through in a series one after another. But many times as engineers, we work in bits and pieces. So it's totally okay to run optimization separately, or manufacturing simulation separately, or the FE analysis separately. You can bring in the part from somewhere else and just run the manufacturing simulation to check, if I make this part, what will happen. So this is in ideal world, the entire end-to-end solution, which can be used in bits and pieces. So this is a good example about what is a smart design, right? What is the simulation driven design? The same exact bracket designed for different manufacturing processes, from conventional single draw casting to powder bed laser melting with additive manufacturing, or maybe it's a hybrid method where I get the sand mold 3D printed and casting as a manufacturing process, or I can go with the machining, right? This is it's a 3-axis or a 5-axis mill or 9-axis mill and come up with a design. So same bracket can be designed and also manufacturability checked for within the single solution. To achieve that, there are different manufacturing simulation techniques or solutions, from metal casting, metal forming, injection molding, extrusion, both for metal and polymer, additive manufacturing, and polyurethane foaming. Again, these are the for design engineers, mechanical engineers to be used very early in the design product development phase. At this point, I want to ask Taylor, who's coordinating for us today, to launch a quick poll to see how we do simulations today, how the attendees today are doing the simulation. Taylor, can you launch the poll, please?
Yes. 1 second.
All right. Now we'll give few minutes to kind of see. Somehow I'm not able to see the poll questions or the percentage about who's doing what. So Taylor, feel free to kind of fill me in on what the result on the percentage. All right. Oh, there you go. I can see it now. For me, I'll definitely right from the. So the poll is, how early do you incorporate simulation in your product development process, right? Also just pick one of the answers. The 3 options or 4 options: we don't use simulation during testing and validation, midway through product development, right from the concept and the design stage. All right, hopefully everyone will get to the poll. All right, I'm good. I think Taylor, we're good. Well, we can close the poll and we can move forward. By the way, feel free to type in your questions if you have. We'll try to address those questions as right away or at the end of the session. Now, I'm going to start diving a little bit deep into the discussion today on manufacturing solutions. Until now, we saw how the design optimization, topology optimization can come up with designs which are manufacturable. But what are these manufacturing feasibility tools, sir? Let's start kind of diving into the Inspire Cast, which is our casting solution. So it's a complete casting solution from filling analysis to cooling, cycling, and warpage. It is a temperature couple. That means we are running both flow for the molten metal and the temperature for the entire system. It can be die, it can be tooling, and it also can have the cooling lines or the lines you can see from the screen. I think there's a video. Let's play that video. And when it comes to the cooling or the solidification part, the Inspire will start coming with the results for the porosities, hotspots. We can run the tooling analysis. We can run the cooling optimization. At the end, when we run the warpage analysis, it can come up with the deformation and the residual stresses, which, by the way, can be used for structural analysis. So as an engineer, I'm also want to know, if I manufacture this part, if I use this part for my final assemblies, final geometries, how it is going to perform, what kind of material properties I will get. So we can export this deformation or residual stresses results for the structural analysis. Many of our companies do this for the crash or the drop test to see this cast part, how it will perform in the real assembly. So so there are 2 ways casting solution is being used. one very early by the designers in during the product development phase. Coming with the design in few minutes, few seconds rather. I want to come out, I want to find out the porosities. I want a quick preview about the where the porosity will be. I want to run a quick thickness analysis. The rib structure. You have 1 millimeter, 2 millimeter ribs. What will happen? Or the draft angles for the mold opening. 1 or 3 degrees is very common draft angles for in casting world. We can run quick analysis on those. And the later stage, we can run complete CAE or the manufacturing simulation for the part, for the entire part, where we can start adding more components in the casting process, such as covers, chillers, risers, sleeves, overflows, and all that stuff. Or you can bring all those parts from the external setup as well. So you're working with the foundry, and they have all this setup done for your parts, but you want to really quickly check if I use that setup, what will happen if when we start actually pouring the metal. So before we actually start spending time on the tools and dies and metal, um, on the foundry side, we can identify the problems. On the design side, these are the very typical workflow processes. You can see as a porosity preview, that's where we can identify the areas where the porosity might be. So there are two options as a design engineer. I can go back, make design changes to take that porosity out of the part or avoid the porosity, or I can start using some like risers, for example, to take that porosity out of the part. On the advanced analysis side, there are four different processes that Inspire Cast supports. HPDC, high pressure die casting, low pressure die casting, gravity, tilt pouring, sand casting, investment casting. These are the very typical casting processes. It don't have to be the expert in casting, or don't have to be a manufacturing person all the time to use these tools. It's a very easy to use tool. If you happen to use Inspire, uh, you know you can watch some videos for 2 hours or half a day, or go through a quick training session online and start using these two solutions. I think the most difficult part for anyone is understanding some of these results and implementing back to their own design, and that's where Team D3 and we as Altair can come into picture, kind of hold your hands, help you, and kind of go through your first processes, first few projects. Now, second part is Inspire Mold, which is our injection molding tool. It's a complete injection molding tool um, based on Inspire platform. Again, it does a filling, packing, cooling, and warpage analysis. For the filling, we can identify the flow patterns. You can get the temperature flow front for the part. Once you start packing method, find out the sink marks, right? Or when it's a cooling solidification part, find out the well lines or of the mold, or the cycling analysis for the mold. And at the end, use the warpage, complete warpage analysis with fibers to understand the deformation. And again, we can take this data back to the structural analysis if we need the material properties. Now, it's a what we call as a hybrid solver. It runs super fast. The way the solver is based on, it needs very little mesh. As engineers, I don't want to spend time on setting up or the meshing these parts. Something I want to take my part, set it up as quickly as possible, and run the simulation and try to understand what these simulations mean, what these red colors or blue colors are telling me. That's where I want to spend more and more of my time, right? So we have a complete automation done for the injection molding. It's very fast and it's very accurate. Now, there are two modes even in the Inspire mode. As you can see, there's a basic mode for design engineers, quickly run simulation, or once the design is finalized, go to the next step with the advanced mode, where you can start adding more and more components. For example, runner systems or tooling, or the quick check the molding window, or start adding the more process parameters and run the complete detailed simulation from filling, cooling, warpage analysis with fibers on my part. So you can see it depends. The same engineer, same designer can be using these tools either very early or during once the part is finalized. Same exact tool works in both ways. And another way you can notice from Inspire cast to Inspire mold, the workflow looks very same. From for the icons, from the buttons. So the learning curves is very short for all these manufacturing solutions. Now, to quickly show some of the results that we can get from the injection molding analysis, we can go into the hot runner filling system, cold runner filling system, get the sync mark predictions, confidence level for the field. It's kind of go from a 0 to 1, and that's the level. Imagine like percentage level. 1 is bad, but about 0 is good. Now, the next tool I want to talk a little bit about is Inspire Polyfoam. We all use cars, right? We sit on our driver's seat and feels nice and comfortable in our own kingdom. Those car seats, and we hold steering wheels. We have a nice dashboard in the front. We have nice side panels on our doors. Those are all foam made of from the foam, polyurethane foam, and that's what we interact daily. Now let's take example of the car seat I mentioned. Right, the car seat have multiple purpose. Of course, comfort for the driver, passengers in the car, but also it's for the safety purpose. In case of crash or of the car or the side impact, it has to absorb some of that energy. Right, now the polyurethane foam acts as a cushioning or the foam in that effect for in those cases. So we can predict all that analysis. Now, the way the polyurethane foam, let me give another example, very easy to understand. On our homes, we have an insulation material between the walls. We spray this polyurethane liquid and then it kind of solidifies in few minutes or few seconds, right? That is polyurethane foam. Now, the most important part, you don't want to spray it too much, otherwise you'll start getting bulging in some areas. You don't want to have a pockets, air pockets in those. Maybe you don't want to put too less amount as well, because otherwise you get lip pockets and the bad insulation in that case. That's exactly what this polyurethane foaming simulation does. A complete filling, foaming, and curing analysis. I'll give an example. All the many components in the car, many components in the refrigeration units are using this. Second, or the next application is electronics. Many of the electronics world in the as a they call potting analysis. If you think about, you are adding some material on the electronics assemblies components over the PCB board, so it doesn't get shake. Good insulation. We can also simulate that entire component. Um, you Another part of that is material characterization. The way the materials are built for polyurethane is a mixing two different chemicals. That entire process can be simulated using AI tools within the tool. In the past, someone has to go to the lab, mix the materials, try it out, and see if it works. Now that process can be automated using this AI-based material characterization tool as a part of the polyurethane. A few examples where it is being used. As you can see, the refrigerators is a really good application to start with. All the insulations, I would say 9 out of 10 refrigerator companies are using polyurethane foam, Inspire foam as their tool for the solution. PCB potting is another area for the polyurethane foaming solution. You can see you put the potting material in, it solidifies, it raises. Now, the most important part is you don't want to add too much or too less. Too much, that means you're going to create a lot of stress on the components. And that part, how much material to add, where to add that material, how to spray that material is all can be simulated using a polyurethane foaming solution. Same thing you can on the seat industry, right? Or the automotive industry is important for that part. The next tool I want to talk about is Inspire Form. It's our complete forming, metal forming simulation tool. From feasibility analysis to die design to try out. Now, when we talk about the feasibility, is very early design. As a design engineer, I have a component in mind I want to manufacture with stamping, right? I can run quick feasibility simulation, really one step, we call one step simulation, couple of button clicks, and it will come up with the analysis for the formability defects. We can try for the nesting, and then we can go to the next steps with adding a little bit more complexity to the setup, from creating a die design for to understand the spring backs to uh, or you want to improve the process parameters for the tryout with complete progressive dies or analysis optimization, or the compensation. The compensation is, at the end of the process will get maybe deformed part. How can we avoid the deformation? Can I pre-compensate that part? This is a good example of one step or the feasibility check. I have this component. I'm just selecting the different surfaces on that component, also defining my typical holes, or just clean up the geometries. There are different geometry cleanup tools within Inspire portfolio. There are different geometry tools. It's not a CAD tool, but it has CAD like features which can be used to modify the geometry or run some DOE analysis. Quickly check, I have a hole from 1 millimeter to 10 millimeters. What's the best shape or the size for that hole, depending on my design criteria? That entire analysis, that entire study can be run in the background using Inspire DOE studies. The next step is my complete die design, where we have a component. Now I'm assigning the die design component. So we're defining the trim faces here. We define the flanges. So if we need to, if there's a symmetry, we can take the advantage of the symmetry of the part, not in these particular cases. And then we need to defeature some of the holes or the rivets or the chamfers. We can remove those faces. And finally, we can start setting up the die for the die design. The next step is a complete tryout, the complete setting up the entire setup for my progressive die. Starting with, again, you can see from the user interface, it's a left to right or top down approach. Start with the blank face. We define the blanks, we define the constraint, define materials, and then it's a single action or multiple action that die, and we start adding more and more of those process parameters for the simulation. Make it run a little bit faster. Once my let me once my die is set up, I can quickly run analysis. Now look, getting into the result visualization. It's a single action die I set up, so we can look into the formability, the thinning, the wrinkles. If you want to find out, all that can we find out using Inspire form. Now, another reason why this we call Inspire as a platform, and all these tools are part of the Inspire platform, is it's not just running up one particular design or coming with a design or manufacturing, right? It has to be kind of connected workflow. So imagine this is my oil pan. I start with the topography optimization, right? It's still a sheet metal part. So I want to find out what rib structure I can use, and depends on my loads, and in this case oil pan, or it can be model analysis. The tool will tell me how the rib structure should look like. And from there, I come up with a most optimal design and run quick feasibility check for the oil pan. And once that kind of I'm satisfied with the design, I go to the next level of creating the actual die using the Inspire Die Designer. From there, I can run a complete tryout simulation on my oil pan, FDL, FLD plots, and time history plots, thinning. I can define. If I'm happy with it, now I go to the next step where actually I'm working on the die side. This is a die will be casted, so I can run a quick casting simulation on my die to see what kind of densities I will get. If I'm going to get porosities or defects on my die design. And if there are, then I can, in this case, I use 3 risers to take the porosity out of my die, which is manufacturable. And finally, take the designs for the next step of the entire simulation. For this oil pan, I want to put that into my car model for the crash analysis. And we can export that data for structural analysis, crash analysis. In this case, it can be radios or OptiStruct, which is another set of Altair solutions. The next two I want to talk about is Inspire Extrude. It's a metal extrude and the polymer extrusion process. On the metal extrude side, there are simulations to predict or analyze the node cone. It can be both steady state as well as a transient analysis. We can learn about the die filling. It can be single cycle, multiple cycle solutions. It can also run the stress analysis for the tools. There's a solution called SimSolid. It's a meshless technology that we implemented within Inspire. So very complex geometries, forms, you still don't have to mesh it and run structural analysis on those parts. The next is a quenching analysis, run for the part. It can be elastoplastic voltage analysis. We can work on the grain size or the quench factor for the quenching simulation. And finally, optimization, the die optimization or the bearing design optimization can be done as a part of the metal extrude simulation. The next one is a I think let's go back and talk about some of the applications of the defects that it can predict. It can predict the profile distortion, unbalanced bearing wear, die wear. It can also do the weld defects when you get this kind of unmatched flow for the material coming out of the die. It can find the seam welds issues. It can find predict the grain structure, overheating and the profile quality at the end. It's the surface quality prediction. We can export the complete report of the die in this particular case. The next one is a polymer for Inspire Extrude for polymer extrusion. Very similarly, it runs the analysis for the single profile extrusion, co-extrusion with it can have inserts for the prediction. Now on the prediction side, we're talking about the swelling effects, profile distortion. You can look at the material interface, very similar to metal, where we talk about weld seam lines. And also do the pressure or temperature resistance time analysis, which can be exported for the structural analysis to see. All right. Now, this is all great, right? We talked about Inspire Cast for casting simulation, Inspire Mold for injection molding simulation, Inspire Form for stamping, forming analysis, Inspire Extrude for our metal and polymer extrusion. One thing I also want to add is AI in the simulation tools, AI in the manufacturing simulation. So as a engineers or the manufacturing teams, we have tremendous amount of data that has been created, generated over the time. How this from the sensors or maybe manufacturing simulations over the time. Can I use this data to tell these AI models out there and predict the analysis, predict the failures just using AI tools? Absolutely yes, and that's what a lot of companies are started doing and exploring the areas where the historical data from the simulation is fed into the Inspire, the physics AI as a tool name. It trains the tool, and next time you have a design changes or a component comes in, you can use that trained model to predict the simulation, predict the failures. Now, in this case, imagine you don't have to run anything. You don't have to run meshing. You don't have to run actual analysis. You're running just the AI in the background. The time saving is tremendous. Here, just from a traditional analysis, we run 3 hour, 4 hour simulation runs with creating mesh in the background and all that. With the physics AI tools, we can predict the same exact details within like 30 seconds. So it's super fast, super accurate, and it's time saver for that. So if you haven't done that, used it or explored it, I will definitely recommend to use some of these physics AI solutions for any manufacturing process. So now, four takeaways I would say from my presentation today is uh, empower yourself. The tools are there, the designs are the solution for designing and manufacturing are available for there. Use it for the coming with designs which are manufacturable. Optimize very early. Use this generative design, this generative AI tools very early while you are designing the part to predict the failures for manufacturing, for AP analysis, and work on those. Maybe it's as simple as changing the rib thickness, and all your manufacturing problems will go away. Use these AI tools that are available to predict you for those predictions. Now, I always say to my engineers is constantly track cost and performance, right? We go back and forth on a particular design, particular manufacturing iteration. Maybe it's a time, but time is money. And the I think I gave an example earlier is one of the companies, automotive companies, trying to reduce their time cycle, uh, production cycle from 3 years to 15 months. Right? And it cannot happen overnight. It has to be done using the smart tools, smart engineering tools, from designing to manufacturing, and that's exactly what these tools help you to innovate. That works. So I think as I finished early. If you have any questions, feel free to ask those questions right now. I'm here. While you're going through the questions, asking me questions, Taylor, I would suggest, let's run another poll to see what kind of follow up, or what the interest level is for our team, our attendees today. So the poll question here is, what is the main benefit that we are seeking from a simulation from the manufacturing processes, right? It can be reducing defects, waste, improving design efficiency and speed, lowering production cost, enhancing sustainability, faster time to market. In my opinion, all of the above should be one of the options as well. It's my fault I didn't put it, but you can say everybody wants to reduce defects and waste, and we also want to quickly design that's fast and that's efficient design. Feel free to type in any questions you might have in the chat window. I'll happy to answer any of your questions around today's topic. All right, Taylor, do you see any questions coming through?
We do not have any in the Q&A, no.
Okay, that's fine. Um, Again, thanks for joining today's call, everyone. As a follow up, I'll definitely recommend you to download Inspire, connect with the team D3 as a follow up, and maybe you want to dive deep into a particular topic. So thanks again, and have a wonderful day.